Hi everybody, Mr. R here, making sure we're live and going. It does appear that we are. Greetings. And we're going to kick it back where we kicked it the last time. Kick it back where we kicked it last time? I don't know. We're doing a lot of kicking. I don't get it. Starting up where we started last time, as you can see behind me here, with Weather Theory Part 2. And so that's what we're going to do is pick this up where we left off. We'll start here by just taking a look at some of the weather that we have here in the country right now. This is the XM weather that we're looking at. Here, just refreshed on your screen, and you can see that right now, and again, I know that this is not the time that you're looking at it, but you can kind of see that we have some stuff sort of moving in here to the Pacific Northwest. Normally, that's going to be a weather maker for Aspen this time of year as it kind of moves in here from west to east. And then it kind of pushes southward sometimes. Sometimes it cuts above us, sometimes it moves below us. But we're going to start to see more of a change in where our weather comes from, because as it begins to warm, we will see more and more of our weather coming from the south as it pushes in here, this warm, moist air that's going to be replacing some of the cool, moist air moving in. And as we go seasonally from spring into summer, we'll see this kind of this monsoon action where this moist air moves in from the south, and it moves in like this and then pushes across the plain states. And this is that type of thing that can bring a lot of weather to the desert southwest as well as to the midsection of our country here, and parts kind of to the east. So that's going to be a thing that we're going to be keeping our eye on here as we start looking at the weather. Remember, as pilots, part of our responsibility is keeping that rolling 5-day forecast up in here. So remember that. Here we go, back here to Weather Theory. Remember that as we climb here from sea level to altitude, we lose approximately 1 inch of atmospheric pressure per 1,000 feet that we climb. We also lose, from a temperature standpoint, approximately 2 degrees Celsius for every 1,000 feet that we climb. So a standard day here in New Orleans, 15 degrees C and 29.92 inches of mercury, or 1013.2 hectopascals or millibars, is going to be equivalent to a 5 degrees Celsius day in Denver, with their actual pressure of being 24.92 inches of mercury. Now, remember that when we talked in the instrument section and we were looking at our altimeter, remember I said that all of the altimeter settings are calibrated for sea level. So remember, you're not putting in the actual pressure that you have there. You're putting in a calibrated number into your altimeter, into that Colesman window for your altimeter setting. So it's calibrated for sea level. Okay, so that's, just remember, that's how that works. We look here, we have already talked about the performance, and we also know that at sea level we're going to wind up with better performance all the way around. Get better performance from the engine, better performance here from the propeller and the wings, because the molecules are so much closer together. And you can see here that this particular aircraft, the ground roll is 745 feet. You will notice that at 8,000 feet, or in Aspen, it's double. So what does that mean? That means that your performance in most cases is cut in half when you get to Aspen. It is one of the things, my children, that makes flying in and out of Aspen a challenge. But remember this, you learn how to fly in Aspen, you can fly almost anywhere. So, the altitude in the human body. Remember, 78% nitrogen, 21% oxygen, 0.9% argon, 0.1% everything else. Just know that not only does the aircraft performance decrease at altitude, the human performance decreases at altitude as well. It's why that we have to have supplemental oxygen when we are pilot in command of an aircraft. Anytime that we are at a pressure altitude of 12,500 feet for a period of more than 30 minutes, or any time that we are at or above 14,000 feet, we have to be on supplemental oxygen, and at 15,000 feet, we have to offer that oxygen to the passengers in our unpressurized aircraft. It has to be made available. They don't have to use it, but it's got to be available to those passengers at a pressure altitude at and above 15,000 feet. At a pressure altitude above 17,000 feet, like that, most of your passengers are going to have a sleepy time during your flight. So just kind of keep that in mind. The use of oxygen is a big deal. And also that use of oxygen from a physiologic standpoint, especially for flatlanders, is going to be a thing that you really have to consider, especially flying at night anytime you're above 5,000 feet. So if you haven't been acclimated to the altitude for a while, it's a good idea at night to be on oxygen when you're above 5,000 feet. It helps with your vision, it helps with your decision making, it helps kind of stave off a little lethargy there as well. So keep that in mind. Winds and currents. We know that when those areas of pressure change, as we discussed last time, and that air moves from one place to another, we call that wind. So that's where we feel the effects of the molecules. That's what we feel. That stuff that kind of pushes us back, that stuff that moves our hair around, is the stuff that we know. We know that's the molecule, because we know it's all about the, thank you. So wind patterns, we looked at some of the wind patterns earlier in some of the maps that we looked at there before. One thing to keep in mind is that when we look at high pressure systems versus low pressure systems, high pressure systems normally are going to be associated with better flying weather. Low pressure systems and low pressure areas are normally going to be associated with not as good flying weather. So better up here, we have better, and we have, not as good. So remember, high pressure normally associated with better flying weather. When we look, remember what we talked about here also, is that with these low pressure systems, that air is moving in toward the low, it's rising and it's circulating counterclockwise. Remember that with the high pressure systems, at these highs, these things are going to be circulating down toward the ground, and they're going to be going clockwise. So remember that, because we're going to be talking about how best to fly around systems like that if you need to, if you're looking for a tailwind. Convective currents, these are going to be things that tend to cause bumpy flights, because this is rising air. Remember convection, the convective currents that are rising. It is the thing that cools that air, creates those clouds, and as I mentioned before, these light fluffy clouds that look like they'd be so much fun to fly in can sometimes be a bit lumpy. So when we look here at this is why I wanted to show you this. Is because if you look here at this, the counterclockwise movement of a low, and then you look over here at the clockwise movement of a high, it's kind of like putting you right there in sort of a turbocharger. So if you're flying south of a low and north of a high, south of a low, north of a high, then you can expect a tailwind. Now, if you're thinking, okay, that's great on the outbound portion, but now then I want to come home, what's going to be the best way to go? Well, you can look at this and you can say, well, I could do this a couple different ways. If I'm coming back the other direction, I could come down here just south of that high pressure system, or I could come in here where I'm going in north of the low. But remember, which system is generally more associated with better flying weather? Okay, which would it be? It would be the high. So all things being considered equal, I'm going to skirt the southern edge of the high pressure system to try to get that tailwind coming in here to move me there, because I should expect better flying weather that way than if I were to try to take the northern route around a low pressure system. So there's that. We talked about this convective bumpy stuff, and the one thing I wanted to show you here as well is that here is this rising air, this air of convection, and now here on this other pane above this is that you can see that the pilot here is above the tops of these cumulus clouds. That's where you want to be for the smoother ride. When you have those times where you have the cumulus cloud buildup, you want to try to be above those clouds for a smoother ride. The effects of obstructions on winds, we'll look at those here in just a second. Remember that first thing that I showed you out there between the Pacific Ocean, New Mexico, and Farmer Green Jean's wheat field out there in Kansas, is that as you look at this, you can see here that during the daylight, you have this where this air gets warmed up, creating a void. The cooler air moves in over here from the ocean, and that creates what we call a sea breeze, where the wind is coming in off the ocean. Well, what happens at night? Well, at night, what happens is that the land tends to give up the temperatures more so. So this is going to be cooler, whereas the water is going to maintain that temperature better. So now the water is actually going to be relatively warmer than the land. So now you get the opposite flow. Now you get this air that moves vertically up above the water, creating a void here that is going to be filled by the cooler air moving in here from the land. That's called a land breeze. So that kind of shows you how that air moves. Now then, we're talking about currents that can be created by varying obstructions on the ground, various orographic type of things that we have on the ground. And this can be a real kind of a serious thing, because this is a big situation that you have, especially in the desert Southwest, where it gets really, really hot sometimes. And some cases you can have, like if you're flying into an airport over a golf course, let's say that you're coming in and here you are over this green manicured golf course, and then just before you get from that golf course to the airport, you come across a brown stretch, or you come across a mall parking lot that's black, let's say. Well, what can happen is that you're all set up on your approach, then you get above that dark surface and it balloons you up. So you kind of have to be ready for that to be able to then adjust your flight path so that you can land correctly. The opposite is true. If you're coming in, like here's the desert right here, and then here's a golf course, let's say, or a big pond, and then now you have a cooler water. So now here you are, you have adjusted this over the hotter air. Now it starts to cool off and that air begins to sink, creating that downdraft. Well, you got to be ready on the power to make sure that you don't fall below your glide slope to come in to land correctly. And that's what this illustration here is trying to show you, is that here you come in, you can see the airport there, and you've just come in off a parking lot of a mall or whatever it's going to be, over this little pond before you get to the airport, and that's where you might expect to feel some of that cooling, sinking air if conditions are relatively stable. If you've got a big wind coming in from one direction or to the south or whatever, it may not matter as much. But in this case, if you're looking at this, just if you have a relatively stable atmosphere and it's just simply the temperature that is causing the issues, then this is going to be a thing that you really have to be prepared for. Coming in and around buildings, when that wind is coming in here off the hangars or whatever, you have to be prepared for the fact that you're going to have air in a blender. The same thing happens, guys, when we're flying into Aspen, is because we normally have a breeze from the west or the southwest that comes through those canyons, and when it clears those ridges, it just tumbles. And so especially when you come into Aspen the way that we do in that valley, so you have a ridge here to the west, you have a ridge over here to the east, and it just creates this tumbling effect of the air. So you really have to be ready on that throttle to add altitude, to reduce throttle if you start getting lifted up. That's why I make such a huge thing about keeping your hand on the throttle anytime you are at or below 500 feet AGL in our neck of the woods. You never take your hand off that throttle, okay? anytime you're in a training aircraft. It's different if you're flying a big jet and you get to V1 and then you take your hand off the throttle because you're at full throttle. You put your hand on the control to make sure that you don't, because at V1 in a high performance jet, you're at the point of no return. You're going to take off regardless. And so that's where it is, because you've run out of runway, you're going to take off. So that's why you put your hand over here on the controls versus the throttle. But in a training aircraft, go back to what I said before, hand stays on the throttle. Here again, welcome to Aspen. By the way, there's your runway, okay? So we have to be prepared for that. Low level wind shear, this is a big thing, LLWS, low level wind shear. This is a thing that normally can happen. We normally think about this anytime that we're 3,000 feet AGL or below as being that low level wind shear. That wind shear is the sudden or drastic change of the air direction and or velocity in that wind shear. It can happen horizontally, it can happen vertically, it can happen at an angle, it doesn't matter, and it can come from nowhere. There are certain types of weather phenomenons where we might expect more probability of wind shear than other times. For instance, when those winds are greater than 25 knots over our ridges to the west and the southwest, we should expect some form of wind shear and turbulence anytime that we're below those ridges. Even sometimes when those winds are above 30 knots, 35 knots blowing above our ridges, we can get up into the turbulence even when we're at 15, 16, 17,000 feet from that, because again, that air just pushes up and over those mountains. So we have to be ready for that. Clear air turbulence can be the same thing. All of a sudden we're flying along and the next thing you know your head is at the ceiling. It's why we wear those safety belts. It's why we snug those bad boys up, is to keep from getting bounced around in the cockpit, especially when we're flying in and around the mountains in training aircraft. So we snug those things up. It's why we have the bubble canopies on the Diamonds. It gives us a little extra margin of room to kind of get moved around without smacking your head up on the canopy. We also have the bubble canopy gives us a little bit more shoulder room as well, just so that it's all towards safety. So low-level wind shear, know what it is and know when you might be able to find it. This is an effect of a microburst, which can be a type of a low-level wind shear, because you can see that what happens is that when you get this downburst down, that wind goes everywhere once it strikes the ground. Think about some time, and if at some point you want to see if this actually works, you can take a water hose, take a cup of water, something like this on your driveway or the street or whatever, and just take the cup of water and just pour it on the street. What happens? When that water hits the street, it goes every direction, right? So omnidirectional, and it spreads out away from where the stream hits something hard. Same thing happens with the air. Here, that air moves out in this downdraft. That air moves out in all directions. So when you're taking off, it's going to be a headwind. When you're right underneath it, it's going to be pushing you down. Then, as you start to fly out of it, now you have a tailwind, and you may not have enough power to climb out of that. So we have to be extremely careful when we're taking off or landing when we know that there is a weather system close to a mountain airport. Any airport for that matter, but especially a mountain airport. And we look here, wind and pressure representation on surface maps that we have that kind of tell us about where our pressure is. So if you remember what I was telling you here before, is that 1013.2 is equivalent to 29.92 inches of mercury. So now you can see here that 1016, 1024, 1028, this is higher pressure here relative to 29.92. 10.8, now it's starting to become lower pressure here as well. So that's what these isobars are telling us. The isobars are going to be these spaces that kind of outline what the pressure situation is around our maps. And I'm not 100% sure. I don't know that I've ever looked at these maps to see if they, I don't think it does, but I'm pretty sure on the pressures here, we'll be able to see what these are on our surface analysis maps. So if we look at like the latest surface analysis map, you can see here, this is a representation of some of the isobars. You see the H, that's a high pressure system over here. That's at 1020, so we know it's higher than 1013.2, which is 29.92, which is standard. And so we know it's a little bit higher than that. Here, just right across from it, we have a little bit of a lower pressure. This is 1011, which is lower than 1013.2, so it's a little bit lower. We don't have a huge low pressure system here right now, like you might see coming up in hurricane season, but there are. So again, remember that these pressure systems, it's all relative. Because, you know, 1023, that can be a pretty decent sized high pressure system. 1026, that can be relatively decent high pressure system. So that's what you're looking at here, is you're looking at these isobars. This isobar here is saying that here around this area, this is where the pressure is approximately at 1029 or 1020. I can't quite read that. So that's kind of what those look like. Another thing here that we look at is when we're looking at these weather maps are some of the symbols that we'll see on these weather charts. So for instance, if we look at these, they're basically telling us about wind, and it's giving us direction and velocity. So if we think about this as being an arrow, so if this is an arrow here, this arrow is like this, and these two bars are kind of the fletchings on that arrow. Okay? So if we look at this, we know that we have a wind from the southwest at 20. Because when you have a bar like this, okay, so here's your arrow, and then you have the big long bars. Each one of those long bars is going to be 10 knots. If you have a small bar, that's going to be 5 knots. But if back here you've got a flag, like one of these big flag thingies right here, that's 50 knots, okay? So that's 50 knots. So if we look at this, this one is showing that we have 50 plus 50 and 5, so that's 105, well, it shows it right here, I'm sorry, 105 knot wind. That's brisk, okay? This looks like golf. Yeah, kind of. But what it means is that you have a wind from the north at 50 knots. Okay, here's a wind from the east at 35 knots. Here's a wind from the northwest, which is barely a wind at 5 knots. And if there isn't any kind of a fletching or that indicates direction or velocity, then it's going to be winds are going to be calm, and that'll be the double birdie looking sign right there. Okay, so that's kind of how that works. Atmospheric stability, what does that mean? Are there times when our atmosphere is more stable than others? Yes, normally under a high pressure system. Are there times when our atmospheric stability is going to be less stable? Well, yeah, that can be when we have a lot of convection out there, you know, when we have a lot of air that's moving up and can be somewhat unstable. Low pressure systems can create that instability as well. Some fronts, some of these large air masses that move around can also create some of the instability there as well. So when we look here, atmospheric stability is like a big deal here for us. One of the things that we show is that we show here an average lapse rate of a temperature here is approximately 2 degrees Celsius per 1,000 feet, or that equates to approximately 3.5 degrees Fahrenheit per 1,000 feet. That's what we would call the standard lapse rate. LAPS, standard lapse rate. Now, again, I'm assuming you guys are writing all this stuff down. So that's kind of it. In some cases, we can have a dry adiabatic lapse rate that has unsaturated air that might create a little higher temperature drop the more we go. And then again, if that air is moist, that lapse rate may be less than 2 degrees. So the dry lapse rate, you're going to have a faster temperature change. A moist adiabatic lapse rate is you're going to have a slower temperature change as you climb. Temperature inversions. Normally, as the air rises, it gets cooler. In some cases, we have a temperature inversion where warmer air is trapping colder air down below. And so in that case, as you climb, temperature can actually increase. In those temperature inversions, one of the big things that we want to know is that as you climb through the top of the cold to the bottom of the warm, that's one of those places where you can expect wind shear. So just keep that in mind. We have also moisture and temperature. Remember that the molecules that we have are kind of spread out, you know, as the altitude increases or as the temperature increases, they sort of spread out. When that happens, you can have water vapor, so little droplets of water that can form between these molecules there. And we measure that in terms of humidity that we have in the air, how much moisture can there be in the air? Well, remember, warmer air can hold more moisture than colder air. Colder air squeezes out the molecules, which is kind of why we see clouds. And it's why that in the mountains, the temperatures are normally drier, or excuse me, that the air is normally drier and we have less humidity than we do here in New Orleans, where we have a lot of humidity. And in that case, we have a lot of the water vapor molecules here in the air. So we have to kind of know that and know what that dew point change is. And that dew point change is that point at which we get to that saturation level where there cannot be any more moisture. And if that temperature drops a little bit and those air molecules get closer together, it squeezes out the water vapor into visible moisture, and we can have fog, low clouds, things like that. Temperature dew point relationship, you can look at this here. We just talked about it. You can read that and see what that temperature dew point is going to be about here for you guys. It basically just tells you what I just told you. Dew and frost, we can talk about how this forms. And again, this is when that air, that humid air is cooled to the dew point and it squeezes out that water. And that's kind of where all that stuff kind of shows up. Fog. We are not going to get into to a lot of the fog stuff here yet, but know that there is, sorry, I meant to change that camera view. Excuse me. Know that there are several different types of fog, and next year you're going to need to know what those different types of fogs are, how that fog can form. When you're flying in the mountains, clearly an illustration like this here at 12-21, anytime that you can have kind of that radiation fog through there, that's going to be something that you want to know about, especially if you're flying to an airport where it could be susceptible to this type of fog, because you may get over there and not be able to see the runway. Pardon me whilst I sip. So then we look at clouds. We're going to cover the clouds a little bit more here than the fog. Clouds, again, a cloud is basically visible moisture. That's what it is. It's water molecules that have been squeezed out of the air, and they make their appearance in the term of visible moisture. So you'll notice here that the clouds, the nomenclature of the clouds is based on height. So if we get here 6,500 feet AGL and below, we tend to call these stratus clouds. Now that stratus can be either a prefix or a suffix. The prefix here in stratocumulus clouds or a suffix here in nimbostratus cloud. This type of a stratocumulus cloud means that it's going to be one of these lower clouds. It's trying to get, you know, kind of this puffy look to it here as well. Or a rain cloud, nimbo here, a rain cloud. Then above 6,500 feet AGL to approximately 20,000 feet AGL, we get into this alto area here, the alto or mid level. And again, it can be a prefix or a suffix. So you have alto stratus, which are kind of these larger, flatter, more horizontal looking clouds, to the alto cumulus, which again, remember, are like those light, fluffy clouds here as well. Above 20,000 feet AGL, this is where we get into the cirro area here. So the cirrostratus, cirrocumulus, and just the straight cirrus types of clouds that we have here. I am apologizing here. I did not know that was on. So these clouds are primarily composed of ice crystals. Remember that anytime you're above 24,000 feet MSL, the temperature is always below zero. So these clouds here, in most cases, are going to be ice crystals that you're going to see here. Instead of some forms of liquid water. When we get into the instrument section of the course next year, you'll understand the reasons why I bring that up. Then, on the right side of this illustration, we get into the nasties. This is where we get into these towering cumulus clouds. And when I say towering, I do mean towering. The tops of some of these cumulonimbus clouds or thunderstorm clouds, they can exceed 60,000 feet. And these things can be monsters. And the energy contained in these storms like this, these are nothing that we want to tangle with. It doesn't matter how big that airplane is. You don't fly through a thunderstorm. It doesn't matter. In fact, we give thunderstorms, the footprint of those thunderstorms, a wide berth. So if you're able to look down at a cloud and whatever that footprint is, we don't want to get any closer than 20 nautical miles around the footprint of that cloud. Now, notice that I say looking down at the cloud, and here's why. When we look here at this anvil type shape here of the cloud, it may extend, and normally we're going to see this as we look from west to east. This anvil type cloud will actually extend out here further toward the east in most cases. And so you'll have that big anvil shape here. You don't even want to fly underneath that 20 nautical miles. And the reason being is because in some cases what can happen is that you can have hail being shot out of the front end of this system right here. And there have been numerous reports of pilots who thought they could kind of cut the corner on a thunderstorm, and they fly underneath this anvil and they get sprayed with hail, and it'll bring down airplanes. So we don't want to mess with a big cumulus cloud. It's just, we just don't do it with these big cumulonimbus thunderstorm clouds. We'll talk more about thunderstorms here coming up. So here, one of the things that I want you guys to make sure that you write down is these types of cloud formations and these types of classifications. Okay, so make sure you have that. All right. Ceiling, we talk about a ceiling, and that's like, okay, if we look outside and we see a layer of clouds above us, well, what's the floor of that ceiling? And we think about that as being an obstruction. Normally when we look at things and we think about looking up, we look at things like different various layers where we'll have clear, we'll have scattered clouds, we'll have few clouds, we'll have broken clouds, and then we'll have overcast. So broken and overcast are a ceiling. Everything else we should be able to fly around, just to kind of keep that there. They talk about a lot of these things here, guys, in this chapter that we'll talk about later, and they bring it up just so that when you see it again, you'll remember that you saw it, and we just don't go to it in a lot of detail. Air masses. When we look at these air masses, this is going to be the thing where we start talking about fronts. Okay, and I want to save the fronts for kind of its own section. So we're going to start talking about fronts. So make sure that you have read the section about fronts for next time. And we will pick this up next time here on this next episode on part 3, picking up here on fronts. Okay, so that'll end part 2. Pick this up on part 3, having to do with fronts. Guys, enjoy.